Hello, everybody. My name is Ben Sigelman. I'm one of the founders at Lightstep. And as Spoon said earlier before the talks, you can think of us as providing what we think is some much needed visibility into the stories that microservice architectures are telling these days. So I'll just get going. I guess I'd start by talking about microservices in general. I think they get a lot of hype, obviously, these days. It seems like we hear about them everywhere. The idea is not new. They, went by other names 10 years ago, and I think what is new is that it's actually starting to happen. I think people are always talking about service-oriented architectures and decoupling things, but in the last couple of years, I think in large part, thanks to projects like gRPC and languages like Go, concurrency was a reality, and microservices finally started to really make sense from a systems perspective. I think that they're here to stay. There's so many advantages, not just system advantages, but process advantages to microservices with decoupling of continuous integration, deployment. Eng teams can move independently, services can auto-scale, et cetera. There are various problems with microservices. They create a lot of friction around service discovery, orchestration, et cetera. What we at Lightstep are particularly concerned with, and thus, what I think about all the time, and thus what this talk concerns itself with, is how microservices break your monitoring tools. This is because monitoring tools are designed to tell stories. That's the point of monitoring tools, is that you don't know why something's happening. You look at your monitoring tool, it tells you the story of what's happening. The problem is that monitoring tools that are scoped to a single process are unable to do that in a decoupled service environment. So if this is a monolithic app, and it has lots of little components as library boundaries, a microservice equivalent might be what you see on the right, with lots of little services that maybe roughly correspond to the sorts of API boundaries you had in packages in your old application. The story that you told in your old application now needs to cross process boundaries. And I think a lot of people who have adopted microservices at scale have run wholesale into the problem that you can no longer tell these stories. Your logging tools don't have correlation IDs, or if they do, the amount of data you're dealing with is so overwhelming that you're unable to actually unravel the chain of events that took place in a given workflow in your system. And so distributed tracing, which is not a new idea. I mean, the first academic papers are decades old at this point, was designed for this particular problem. And I think it's become something of growing importance to companies and organizations that have actually started practicing microservices in a production environment. Long story short, distributed tracing is designed to connect the dots between all of your microservices and tell an unbroken story of what took place for any given transaction. Just to make this a little bit more concrete, I'll show you some examples. One of our fabulous team members, Brandon, did all of the work here. This is instrumentation of etcd. Are people familiar with, well, show of hands, people who are familiar with etcd? Okay, people who are familiar with Raft? And people who think Raft is simple? Okay, right. Oh, nice. You got one guy. Okay, you're hired. Anyway, so Raft is unbelievably complex, at least for my feeble brain. And if you're trying to figure out why it's not performing the way you want, that's a pretty challenging thing. And performing could mean that it's slow. It could mean that there's some sort of unexpected behavior if you're debugging a change. So Brandon added some instrumentation using OpenTracing, although that's not the point of this demo, just to show what this looks like. So to bring this up, I'll sort of bring things out. So at the top level, we have this one. This is a bit like the Chrome debugger or something. You see a timing diagram. This operation took 12 milliseconds, 10.6 milliseconds. I can then say, okay, well, what did it do? And it says, well, it called this client. I can continue down. It's now crossed a process boundary and is on some server, infer1, and I can continue. I can expand this whole thing out, and you can see, okay, this is what Raft is actually doing. So here's a timing diagram going down the stack, and each one of these things can have a pretty detailed payload information saying what's actually going over the wire, and so on and so forth. So if you're trying to debug what was happening here, you see some pretty interesting things, like things are progressing normally. You have this kind of cascading set of events, one depending on the previous. Suddenly things take a while. If you look at what happens, you can look at the log and it says, oh, one message was queued. This is the contents of the message, etc. So if you compare this with a traditional logging system where you're dealing with a lot of concurrency on top of all this complexity, I think it sort of speaks for itself that this sort of technology is valuable. If we look at an example of a request that took a little bit longer, this one took, almost 40 milliseconds, 38 milliseconds, and you can see that there are actually three instances of queuing before we got back to what we were starting with and come all the way back up to the client. Those are 2 host examples kind of in a test environment. In a 3 host example, just to kind of give a sense of the complexity, now we have 3 nodes that are interoperating, and again, you get the same level of detail, and I'm just arbitrarily picking something to expand, but this level of detail is available throughout this entire trace. And when you see production systems that aren't just part of a demo for an app for a presentation like this, sometimes you'll end up with thousands or even tens of thousands of nodes in these traces, and they're very useful for debugging things, right? So I hope I've made at least a quick pitch for why this can be useful if you're trying to understand behavior in distributed systems. Okay, so tracing is great. What's the catch? Why hasn't everyone been using this for the last 5 or 10 years? And the reason is because instrumentation has been broken. Distributed tracing instrumentation is, it's not that the programming task is necessarily that difficult, but it's almost more of a market-making issue and an issue in the open source community. That's really been the gap so far. Distributed tracing instrumentation, it must be explicit. I did a lot of work on distributed tracing at Google, and I've talked with a lot of people who've worked on this in other places. It's maybe possible to do implicit instrumentation of very simple, 2-node, 3-node systems and get reasonable quality, but if you're dealing with a truly distributed system, the instrumentation has to be explicit for the traces to be accurate. So that means you're going to have to actually get your hands dirty and instrument stuff. The instrumentation needs to be decoupled from any particular tracing system. Some systems are better than others for certain tasks, and that is not something that the code owner of a specific open source library knows ahead of time. Like gRPC, for instance, might be used in some really tiny projects and then some really giant projects. And tracing systems for a tiny project are not the same as tracing systems for a giant project. So kind of by consequence, the instrumentation needs to be decoupled from tracing systems. The consistency across platforms needs to be there. Tracing has to work in Go, but it has to work in not Go as well. And so that requires a degree of centralized control over just nouns and verbs and concepts. And coordination has to be possible across API boundaries, not just between processes, but within a single process. And all of this is actually pretty easy engineering work. It's not like it's trivial or something, but it's not that hard. The part that's hard is standardization. And that's where OpenTracing comes in. I don't expect to get through all of the detail on this slide, although if anyone wants to talk to me afterwards, I'm happy to. But on the left are basically benefits that you can get from standardization at various levels of a tracing stack. Most attempts to standardize tracing to date have revolved around encoding, which ironically is totally irrelevant to the main benefits that we could get from tracing standardization. The main benefits in my mind, again, would be API consistency, keeping the instrumentation dependencies small so open source projects can actually add instrumentation without creating some massive requirement that you also use Zipkin or whatever. And again, per my earlier point, allowing tracing libraries to instrument without locking themselves into a vendor. So encoding formats in my mind are actually not that important for standardization. They are important for people who are implementing tracing systems, but that's not in terms of the community, people affected by tracing, those of us who are implementing tracing systems are just a drop in the bucket of the people who would benefit from them. So OpenTracing scope is really focused on APIs. Specifically, I don't have time in this talk to go into detail about what these 1, 2, and 3 actually mean, although again, I'm happy to afterwards if people have questions. The basic approach in open tracing is, let's just take the trivial example of you have a client and a server and they're trying to communicate. It is important in tracing for some portion of the application payload in band needs to have a few tidbits about the trace, just like a unique identifier basically. And what's interesting about open tracing is that it manages to provide a totally abstract API for doing tracing without having any opinion about the specific encoding of that data. So the implementations have full control over how they decide to actually reify the unique identifiers in a trace or any other sampling or probability information they have to pass in band. And open source packages, whether they have to do with RPCs or if they just have to do with flow of control or if they have to do with something else entirely, those packages can use open tracing that's linked into the process without regard for anything specific about the tracing implementation. The implementation, which is denoted by this sort of darker green box here, what it will actually do in practice is get the data out of the process and into its own centralized system, which is intentionally out of scope for open tracing and also for this talk. What's important is that the open source packages and the application code, depending on tracing, have this like 50-line of code library they can code against and get the sort of interoperation that we need in this community in order to provide for visibility. So let's talk about Go. So Go for tracing has a much better looking developer community than any developer community in the world, for sure. Just look around the room. It's like an incredibly good looking group. More seriously, concurrency is the rule. Not the exception, and that means that you're like very quickly forced to care about this. If you're using Rails or something like that, just the nature of the system is to have basically one thing happening at once, at least as far as your process is concerned, and that allows you to kind of cheat on the tracing front. With Go, that's rarely the case. The previous talk was a great example of that, and with that sort of concurrency, it's essential to have a good story on tracing just to get signal to noise at the process level to a reasonable place. It's also more likely kind of culturally, I guess, that people are going to develop Go applications in the context of decoupled architectures. There's no thread local storage. Thread local storage is something that a lot of languages use to pass tracing data from one library to the next. I'm saying asterisk there because I'm sure you guys are familiar with some of the like unbelievable hacks people have done to like get thread local storage into Go. I think Brad Fitz has this thing that like does string parsing of the Go stack dumps to find the Go routine ID and then takes a global lock in the process to like insert into a map. So discounting such things, there's no thread local storage. Context.context is sort of the only game in town. You know, it giveth and it taketh away, as I'd put it. So the rules from the Go doc are that you pass a context explicitly to every function that needs it. Okay, we'll get to what needs it in a second. So that's an explicit parameter that you explicitly write into your code. I'm sure a lot of you are familiar with it, but I can't help myself in just going into this. So so let's talk about functions that need it. Those are functions that might involve state transfer that might move across process boundaries or might involve state transfer that might move across API boundaries, which is, I think, like everything in the world, but I'm not positive. So this reminded me of like Return to Zork, or Zork, I can't even remember. I'm having flashbacks to being 3, apparently. Anyway, but so I hope you all are somewhat familiar, but here's the situation, you know. So with context, like you're writing code, you're in a microservice, there are services above you and below you, there are APIs above you and below you, there's a function call. I guess I need to use context. So I think the answer is that you have to have context in every function call in your whole application, which ironically is what thread local storage does, but I digress. So in defense of the Go overlords, what's not true about what I just said is that you also have channels and things like that. And Go, the benevolent dictators, they decided not to provide any sort of programmatic access to override anything happening in and out of channels, which means that without something like context, you would be basically incapable of doing anything like tracing. And what I do really admire about context is that despite how ridiculous it is, and it is ridiculous, it does make it makes it completely explicitly clear what's happening in terms of control flow in an application, and that's like a really, really valuable thing. And even though it results in like a lot of typing, I think it was probably the right thing. And as a result, at our company, we see a lot of different languages go by, and Go is the one, assuming people have used context, which is becoming more and more the norm, where tracing often just works because people have already threaded this through, and you can just throw the tracing context in there as well. So anyway, TLDR, if you're using Go and you want tracing to work, you'd better use context. And luckily, I think a lot of people are using it for other reasons. So I've tried to go very quickly. Let me actually show a little demo. Are you all familiar with GoKit? It's this project that Peter, I always mispronounce his last name, but he's a great engineer. Anyway, it's sort of like a microservices toolkit for Go. This is an example app of theirs. GoKit supports OpenTracing natively at this point. And just to give everyone a sense of how this works, this demo allows you to use different tracing systems with the GoKit add service, which is a fascinating distributed system that computes the sum of two numbers. It also concatenates strings. It does either of those things. But so you say, okay, I've got a tracer. Is this big enough that people can see it? I'll make it even bigger. So I've got a tracer, which I've highlighted for everyone's reading ease. And depending on some command line flags, I either create an Appdash tracer or a Lightstep tracer. There's also a Zipkin tracer that is not hooked up in this example. And then down below, when that's this bunch of stuff. When you're building your endpoints, you pass a tracer to them. And like that's kind of it. It's like a very simple integration. So to show how this works, sorry. So I'll do Appdash first. So I'll run the service with the Appdash tracer flag enabled. This just tells OpenTracing to bind to Appdash, which is a really nice little tracing system written all in Go. You all might be familiar with it, I don't know. And then in the client, I'm going to tell it to sum 3 and 5, and it succeeds. I'll look at Appdash, and yeah, lo and behold, there's a trace showing this sum call with the client and the server. Okay, great. Now I can similarly bind this to Lightstep, which is just another possible backend for Appdash. I can run the client a second time, and yeah, so it will collect this trace and show something similar. So the point here is just that I didn't have to modify any of the code in this example at all, and the only changes between Appdash and Lightstep were in the main file, and tracing just works across this admittedly really simple distributed system. But the point of OpenTracing is that you only make changes to your main line when you want to change tracing systems, and all of your libraries can implement distributed tracing without respect to the particular system that they're embedded within. Yeah, so just a status report on where we're at. The project is pretty young. It's several months old at this point. I think I've signed a bunch of NDAs, but there are a lot of tech companies that everyone has heard of that are using OpenTracing internally and are excited about it. We have contributors from a bunch of tracing systems, and also from a bunch of companies that are interested in this sort of technology. GoKit supports that out of the box. gRPC integration will happen this summer and is actually really easy thanks to gRPC's bindings. And it's usually pretty straightforward to instrument stuff, and anyone people from Lightstep just raise their hands. If you want to talk to anyone of us after the talk, we're happy to talk about getting contributions and for this. It's actually usually pretty fun. We have a sort of internal joke about tracing as fun because one of our teammates who had never done it before was at lunch, and he has a really dry sense of humor, and he's like, tracing is fun. And we're like, Will, are you kidding? He's like, no, I'm not kidding. So it can actually be really fun to do. You get to learn how a system works in a lot of detail. So check out OpenTracing.io, send me a message. I'll take questions at this point. So. NTP provides as much accuracy as your latency to the closest atomic clock, basically. So if you're on a really, modern local network within a data center and you're dealing with requests that take an order of many milliseconds, then it's fine. If you need to have like single microsecond accuracy, NTP alone is not sufficient within a data center. However, one interesting thing about tracing, which actually helps with the time synchronization problem, is that you have a bunch of global ordering constraints in addition to just raw timestamps. So if you know, for instance, and you do, that the client of an RPC sent something before the server received it, and the server sent its response before the client received that, you can use those sorts of relationships to develop global kind of inequality relationships between different processes, and that in conjunction with time synchronization in a properly thought out distributed tracing system can actually express pretty tight bounds on the relative clocks of the machines in your system. That typically only comes into play when you're dealing with things that are on the order of single-digit milliseconds or less, but it's a great question and a pretty complicated topic. For what it's worth, open tracing per se doesn't need to have an opinion about that as much. It's more of a tracing system implementation problem, but yeah. I would love to do that so much, and I think it's sort of a baby steps thing. It's like that's like the real prize from just being a nerd, right? Is like going and building a distributed debugger that actually works and has breakpoints and such. There's some people actually, Turnkey, which is in this building during the day, they've done some amazing work on providing pretty high fidelity information about Java processes at crash time and allow you to inspect variable state from remote processes in production. And I mean, we're getting closer, but we haven't taken that on yet, although I would love to do that. For what it's worth, open tracing libraries exist for Objective-C and for Android Java and for browser JavaScript. And it doesn't have any, open tracing has no concerns. There's nothing special about clients. The API that it has basically allows all open tracing implementations have to support both an arbitrary key value map of tracing data and a binary blob of tracing data that they can kind of describe in some way, and then there are helpers to get that into and out of HTTP headers or other sorts of transports that you can implement at wherever you happen to be, whether you're in the web client or somewhere else. It's always possible generally to get that sort of metadata into headers. So for HTTP, that's the usual answer. For more homegrown protocols, you can kind of roll your own thing, but whatever has control over the way that the wires actually, the bits actually get into the wire, that's where you'd have to implement that sort of code to get the tracing payload into a header or some other kind of metadata field. Yeah, I mean, I think the answer there is all in integrations with things like gRPC, et cetera. If those integrations take place, I think it's really getting pretty close to what we call it, an order of one integration. It might not, I don't know if it's maybe it's an import and you have to do something in your main, but it's a fixed number of lines of code per application. But we do need those integrations, and we need people. There's the first talk, the great talk from OPSI, talked about gRPC. I think the biggest benefit of RPC has nothing to do with RPC. It's just all the tooling you can do around it. It's not about actually sending data across process boundaries. It's about having things like monitoring tools and service discovery, et cetera, actually work a priori. And this is an example of that. If that Hello World, Hello World app actually used a common RPC framework, and the RPC framework supported open tracing, then it's a totally trivial integration. And that's sort of the vision behind open tracing, is to get people onto standard libraries for things like that. Thank you so much.